We've now introduced the tf-idf model for measuring document similarity. We have this vector of weights that are coming from the tf-idf weight, and we want to go through and compare two different documents when we have these particular vectors. So let's talk a little bit more abstractly to begin about two arbitrary vectors that don't necessarily have this connection with our particular source of vector creation. But in general, whenever we have two vectors, let's call them v and u, and let's suppose that they have n different components. Both of them are n-dimensional vectors. We can define the dot product between two vectors as component-wise multiplication joined together with a sum. Or in other words, the formula that we have for that is v1 times u1, v2 times u2. We do all of those multiplications and we add them together. And that gives us the dot product of the two vectors. However, there's something more important about the dot product of two vectors, which is that it has a visual interpretation that's going to end up being very useful for us. So in general, still abstractly, when we take the dot product of two vectors, what we end up getting is either the norm or the length of those two vectors, however you want to say it, multiplied together, and then also times the product of the cosine of the angle between those two vectors. So that's the sense in which this is visual, is if we were drawing those vectors in n-dimensional space, we'd be getting something that has to do with the lengths of the vectors and then the cosine of the angle between them, which is something we could visualize, which is somehow measuring the distance that these vectors are apart. Now, one thing that we want to do with our vectors is what's called normalize them, which is divide them by their length. So that's what this little symbol means here. The norm of the vector or the length of the vector, that's all it means, is how long is that vector? How far away is it from the origin? And if we take these vectors and divide them by their length, we call them unit vectors because that will make the new vector have length 1. And if we move those over to the other side by a division, or if we replace a vector with a unit vector that has a different length but points in the same direction as that vector, then when we take the dot product of those two unit vectors, what we get is just the cosine of the angle between them. So that helps us mathematically focus on just the cosine of the angle portion, which is what's going to be important to us. But normalizing these vectors has a different benefit for our model that's being derived from the real world, which is it takes the length of a particular document out of consideration. So when we take a vector and we divide by its length in this sense, what we're doing is disregarding the number of words that's in a document. We're making everything proportional to how long that document is. And what that's going to do for us is reduce that error that we were getting when we were saying this document might be a whole lot longer than this other document, and so we might compare them, and of course more words are going to occur in this longer document than they would in this shorter document just based on length. When we normalize things, then everything counts for less in the longer documents than it might in the shorter document. So it's kind of a way of scaling all documents to have the same length. So that's another way to think about taking a look at these unit vectors. And when we compute this dot product then between unit vectors that point in the same direction as our original vectors, what we end up with is the cosine of the angle between those two vectors. So let's take a look at a picture to help us visualize some different things that could happen in two-dimensional space. If we have two vectors that are pointing in almost the same direction, we can visualize the angle between them here. Another thing that comes up is orthogonal vectors, which are vectors that are perpendicular or we think of as being practically different in every way. And then we also have these opposite vectors where they're almost the same vector, but they're pointing in dead opposite directions. That might be a better or more intuitive version of opposite that can happen in general n-dimensional space. But from our specific example, this third picture is not going to be something that we're particularly concerned with because you need to have negative directions in order to point totally in the opposite direction. And we're never going to have negative words occurring in our documents. So this is something that could happen in general, but isn't going to come out of our particular application. We're going to be dealing mostly with these two cases. So we want to think about the fact that documents that are very similar are only going to differ in a couple of components. They may have slightly different lengths based on proportions, but we've taken care of that by using unit vectors, and they might just be off by a couple of words. And so that will lead us into this case where we have these two vectors that are very close together and the angle between them is very small. When we take the cosine of a very small value, we get something that's very close to 1. And so we could interpret that as a probability that these two vectors or these two documents are very similar because there's very little angle between them. That means they're very similar, and that's a high probability that they are similar documents. On the other hand, if we have documents that are very different, that are talking about totally different things, then they're almost never going to agree on any component. And because we don't allow for negative words in our example, what that's going to do is create practically orthogonal vectors. And that means that the angle between them will be close to 90 degrees. And when we take the cosine of 90 degrees, or pi over 2, we're going to get something that's very close to 0. And again, that is a good model for the probability that these two documents are related. If they're very different and they're not using any of the same words, then they're not talking about the same thing. And so we can use this new metric, which is to create this vector of tf-idf weights, and we can take those vectors and normalize them so that they're unit vectors and compute dot products between these vectors and use that as a measure of the probability that these two documents are similar. And that's turns out to be a little bit of a better model than Euclidean distance. So just to sum up what we've done so far, we've looked at two different measures and two different models that we could use to approach document similarity. And we have talked about how these two models take into account some of the things we've seen, like the rearranging of the sentences, the length of the document, and documents that make very superficial changes to a very few number of words. And both of our measures would do pretty decent at handling some of those changes, some better than the others. But we have yet to come up with something that really handles that last case, where we have a Mad Libs type program that's using synonyms to disguise itself as different reviews when in fact they're coming from the same source. However, again, we can use cosine similarity to approach that. And so that tool with tf-idf weights and cosine similarity can really be a useful thing that comes up in data science quite a bit. And last but not least, if you're wondering how the net neutrality thing ended, of course the FCC used the reviews that they had to argue that people supported repealing net neutrality, and it was in fact repealed.